everyone, and welcome back. Today we're going to continue our exploration of intermediate statistics theory and talk about how we can analyze vectors of random variables. Up to this point, we've been primarily interested in analyzing individual variables, with a couple exceptions of where we've sort of vectorized special problems for which we're interested in, multiple linear regression being one of them. As we saw with multiple linear regression, being able to vectorize statistics and probability problems definitely has its advantages, especially when we have several variables of interest. So in this video, we're going to be talking about some important principles that are associated with vectorized statistical theory and a couple formulas and concepts that are actually unique to the vectorized perspective of statistics. So let's start off with a basic problem that is quite easy to understand. Let's assume that we actually have a series of populations. Let's call it P1, P2, all the way down to, say, PK. And obviously each of these populations are going to have a set of parameters, and we're obviously going to be starting off with the population mean of each of these parameters for which we're interested in analyzing, right? So obviously we have several tests that we already have discussed to test the equalities of these means, for example, ANOVA test, Mann-Whitney-U test, and several others as well. But obviously we want to sort of create a theory that compresses these topics in a more easy to understand manner. So what we're going to do is we're going to define a population mean vector, right? So instead of analyzing mu1, mu2 down to mu k, what we're going to do is we're going to create a vector which we're just going to represent by mu, which is going to be equal to a vector with all the means in it. So mu1, mu2, all the way down to mu k, right? So it's a population mean vector, or some people will call it a parameter vector. So parameter vector. So obviously, since we're going to be talking about random vectors, a parameter vector obviously is not a random vector because that's sort of like the statistics and parameters world, right? Statistics depend on the random sample they're associated to, but they're all trying to estimate the same fixed parameter set, or parameter vector in this case, for which we're actually talking about mu, right? So let us assume we gather a simple random sample from each of these. So in particular, let us assume xj let xj be a random variable associated to each population, right? So for example, population 1 could be your blood pressure, population 2 can be the amount of happiness that you have, population K could be how much you slept last night, and so on. And the collection of all those vectors sort of gives you some sense of a person. Therefore, this mu vector, or this parameter vector, sort of encapsulates all the possible means of characteristics that are associated to you. So obviously, let xj be a random sample to each of those variables. So x1 could be blood pressure, x2 could be happiness, and xk could be the amount of sleep that you get. And then obviously we're going to be collecting a sample, sj, obviously belonging to pj. And obviously in each of those samples are going to have some structure. For example, we have the first element of j, which we're going to represent by xj1, the second element of j, which we're going to represent by xj2, all the way out to the nth element of sj, which we're going to represent as xj nj, where obviously the size of the sample is equal to nj, and obviously we need not take the same exact sample size from each of these populations. So obviously, for this particular sample, we're going to have a mean associated to it, and we're also going to have a variance associated to that as well. And as we already know, the sample mean is hopefully going to be approximating mu j, and sj squared is hopefully going to be estimating sigma j squared. So let's work out a couple theoretical things just in case you are not already aware of them. So what we're going to do is we're going to define capital X bar j to be equal to 1 divided by nj times the sum of xj1 plus xj2 all the way down to xj nj. Now here, capital xji or something like that, these are all random variables. So this is just a linear combination of random variables from population pj, right? And therefore x bar j is a random variable, not a number. So is this random variable x bar j an unbiased estimator for the parameter mu j associated to population j? So we can obviously perform an expected value or an expectation of this random variable. And that's obviously going to be equal to, by properties of expected values, constants can factor out, and expected values can distribute over sums and also differences. So we're going to be left with 1 divided by nj times the expected value of random variable xj1 plus the expected value of xj2 all the way down to the expected value of xj nj. Obviously, since all of these random variables are coming from the same exact population pj, all of them are approximating the same exact parameter mu j. So this is going to be equal to 1 over nj times mu j plus mu j all the way out to mu j, and we obviously have nj of these elements, so that's obviously going to be equal to 1 over nj times mu j times nj, and those nj's obviously are going to cancel, and then we have mu j as the final result. And what does this imply? So this means that capital Xj is an unbiased estimator for the parameter mu j, and obviously this logic is going to hold for all j is equal to 1, 2, all the way down to the number of parameters that we're actually analyzing here. So let's see if we can construct a vector that has all of these unbiased estimators within them. So now we're going to create a new vector. So now we're going to define x bar. So this is going to be a random vector, and this is going to contain your x bar 1, x bar 2, all the way down to x bar k. Right, so this is a vector of random variables. And this is what we refer to as a random vector. Obviously, the abbreviation still would be RV, but the context is, of course, slightly different. So now the bigger question then becomes, what is the expected value of a random vector? So obviously, that's going to be the expected value of the vector, x bar 1, x bar 2, all the way down to x bar k. So we're going to be taking the expected value of that vector, and this is going to be defined to be equal to the expected value of the elements of that random vector. So the expected value of x1, the expected value of x bar 2, all the way down to the expected value of x bar k. And we've already proven that x bar j is an unbiased estimator of mu j, so that's just going to be equal to mu1, mu2, down to mu k, and we've already defined this to be our parameter vector mu, and therefore what? That means that the random vector x bar is an unbiased estimator of mu. Here, this is a random vector, and this is a vector of parameters. So when you see this notation, some people will abbreviate it with a hat or a little vector symbol. For example, some people will write it like that, but that just creates more notation to sort of discuss. So this notation obviously is contextually based. The concepts are slightly different, but obviously there are some theoretical similarities between them. Now, let's talk about covariances for bivariate samples. So just a quick review, just in case you forgot this from, say, linear regression. So the covariance between a population set of values x and a set of population values y was able to be found by the sum from j is equal to 1 to capital M of xj minus mu j times yj minus mu, and that should be mu x, and this should be mu y, all over capital M. And this is what we referred to as the population covariance between two numerical populations. And another thing that we also explored before is the covariance of two samples. So in particular, a sample x from px and a sample y from py. And that was found to be the sum from j is equal to 1 to little m of xj minus x bar, and then times yj minus y bar, all divided by little n minus 1. So obviously we should be able to generalize this from sets into random variables. So one can say, generally speaking, how would you define this for random variables? Well, we could say that the covariance between variables, let's call them xi and xj, is going to be equal to the expected value of, and we can write it as so this is going to be the expected value of the product, xi minus the mean of that random variable mu I, times xj minus the mean of that random variable mu j. And obviously there's some algebra that we could perform here, and then we can distribute the expected value over that expression. And once we do that, what will we get? Well, that's obviously going to be equal to the expected value of xi times xj minus mu j times the expected value of xi minus mu I times the expected value of xj plus the product of mu I and mu j. Some people refer to this term as the product moment of xi and xj, and obviously we have just first moments of each of these random variables. Now keep in mind that the expected value of xj and mu j are actually equivalent ways of writing the same exact thing. Therefore, this is just going to cancel out to 0, and we already know that mu j is just another way of writing exj again. So therefore, we have that the covariance between random variables xi and xj is just going to be equal to the product moment of xi and xj minus the product of first moments of xi, and xj. So we have this particular identity, which should be familiar as well. So let us also see if we can approximate some covariances. And we're actually going to be using a different notation for the covariance between two random variables, because obviously that gets a little bit lengthy. We're going to be using the covariance of xi and xj to be equivalently written as sigma ij, right? So it's like a variance between a variable with itself, right? So for example, if you see the notation sigma I, so that's the covariance between variable xi and xi, and that's obviously going to be equal to just the variance of variable xi, which obviously has the same exact notation as we typically would denote it, right? So that's sort of motivating why we're going to be using this notation, right? So, question, what to approximate sigma ij with? That is, what are we going to approximate the population covariance between random variables xi and xj with? So obviously a good choice will be the sample covariance between variables xi and xj. So this symbol, Sij, is going to be equal to sort of like the sample covariance, and this is going to be equal to the sum from k is equal to 1 to little m of xik minus x bar I, and then xjk minus x bar j, all over n minus 1. And keep in mind, xik, x bar I, xjk, and x bar j are all random variables, right? So therefore this is also a random variable, and that obviously is a parameter. So one beautiful theorem, and this theorem actually isn't quite hard to prove, and it's the following. The expected value of the sample covariance between variables I and j actually is equal to the population variance between variables xi and xj as well. Right? So let's just actually go through a proof of something that I mentioned just a moment ago, just to make sure we get it. So if we have sigma jj, what exactly does this represent? So again, this is just an equivalent way of writing xj and the covariance between them. And that's defined as the product moment between xj with itself minus the product of first moments between xj and itself. And obviously that's equal to xj, the quantity squared, minus the expected value of xj, the quantity squared. And you should note that this term obviously is just going to be the second moment of variable xj, and that's obviously the first moment squared of the variable xj. And you should remember from basic statistics that this is just another way of writing the variance of xj, and therefore that symbol is just another way of writing the variance of that particular random variable. Now we're going to introduce a very, very important matrix, and this is called the population variance. Some people call it the variance covariance matrix, but in some sense it's just a covariance matrix in disguise, because the covariance between a variable and itself is variance, therefore you just need covariance in order to define all of them. So the variance covariance matrix is going to be represented by capital letter sigma, and this is going to be just a matrix of all of the covariances of xi and xj. So if we look at this matrix in expanded form, we're going to have, for example, sigma 1, 1, sigma 1, 2, all the way down to sigma 1k, sigma 2, 1, sigma 2, 2, all the way down to sigma 2k, and that's going to continue all the way down to sigma k1, sigma k2, all the way down to sigma kk. Right? So that's going to be our covariance matrix. But keep in mind, the covariance of a variable with itself is just equal to the variance, so you could write this in an equivalent way as the variance of the first variable, and then sigma 1, 2, which is covariance between x1 and x2, all the way down to the covariance with 1 and k, and then we have sigma 2, 1, the variance of random variable 2, all the way down to sigma 2k, and obviously sigma k1 is the covariance between xk and x1, and then sigma k2, and that's obviously going to extend all the way down to the variance of random variable xk, which should be the last random variable in your random vector x, right? So keep in mind, this is the population variance covariance matrix for the random vector x, where x is defined to be x1, x2, down to xk. So obviously, don't forget that that's actually where we're coming from. Now, just a quick note on the variance covariance matrix that if it's not obvious, if you have forgotten some basic linear algebra, is that the covariance between I and j is actually equal to the covariance between variable j and variable I. So if that is the case, that means the covariance matrix, sigma, when we take the transposition of that matrix, we should be equal to the original matrix itself. So that means the covariance matrix is a symmetric matrix, right? So that's always a nice little property there, because that tells you something special about the particular structure of that covariance matrix sigma, which is going to play a very important role later on. As a quick example, let us recall the multiple linear regression model given by the number of predictors. Let's assume that we have actually k predictors here. So we have beta 0, beta 1 down to beta k as our regression parameters, and x1 down to xk to be our regression parameters, and epsilon obviously the residual of that particular regression model for a particular point. So obviously when we vectorize the multiple linear regression model, we're going to get the vector y is equal to the design matrix x times the parameter vector beta, which is going to have our beta 0, beta 1 down to beta k, all the way down to our little residual vector epsilon. right? So obviously X, our design matrix, B, this is our random vector, and obviously Y also a random vector as well. And if that is the case, that means this is also a random vector as well, right? Given some design matrix X, which is typically not taken to be random, but one can consider the case where X is actually a random matrix as well, which is another story for another day, right? So obviously the goal is to find estimates beta hat such that some functional, for example, f of beta hat, and let's define it to be the least squares regression functional, in particular y minus x beta hat, the quantity squared, and let's assume that that's the L2 norm, is minimal. Right? So this is the least squares approach, or least squares regression. Some people will also use ordinary least squares regression as a notation for that. Right? So we should already know that this problem for the least squares regression model actually has a beautiful solution, and the beautiful solution is that beta hat is equal to xtx the quantity inverse times x transpose times y, right? And that's a beautiful solution. It has a closed form, and we've spent quite a lot of time talking about some of the analytical properties of this point estimate vector beta hat. Right? So we've actually showed in particular that the expected value of the random vector beta hat is equal to beta. So if we think about this from the hypothesis testing perspective, beta hat here is our random vector, and beta is our parameter vector once we look at it from this perspective. And also, we were able to prove that the variance of this random vector beta hat is equal to sigma squared times the matrix xtx inverse. Right, and keep in mind that xtx inverse, if you have k predictors, is a k plus 1 by k plus 1 square matrix. Right, so in case you don't remember what this little sigma squared is, one of the assumptions of multiple linear regression is that the variance of y given some particular x is equal to a constant. This is called the homoscedasticity assumption of variance. So that's what that sigma squared is, but nonetheless it is just a constant that has the symbol sigma squared representing the variance of y conditional to a particular x value. But what we were able to observe was that this matrix, sigma squared xtx inverse, actually had the following structure. In particular, the first element was the variance of the random variable beta hat 0, and then the next term was the variance of beta hat 0 and beta hat 1, and that extended all the way out to the variance between beta 0 hat and beta hat k. And obviously the next row was the covariance between beta hat 1 and beta hat 0. And then the next diagonal term was the variance of beta hat 1, for which we take the square root and then we get the standard error of that random variable, and that obviously continued all the way out to sigma beta hat 1 and beta hat k. And the pattern obviously continues down to, for example, the covariance between beta hat k and beta hat 0, the covariance between beta hat k and beta hat 1, and that continues all the way down to the variance of the last predictor, beta hat k. Right? So that was what we realized, and obviously this is going to be a k plus 1 by k plus 1 square matrix. But what is this? Well, obviously this is a variance covariance matrix, right? So this in disguise is sigma, right? In particular, it's the sigma for the beta hats, which are the point estimates of our model for our multiple linear regression model, right? So that's obviously our sigma. But question, how do we approximate that? How to approximate the general sigma, right? So to approximate it, what we're going to do is we're going to let S be equal to another matrix, and this is going to be equal to S1 squared, S12, all the way down to S1k, and then S21, S2 squared down to S2k, and then that's going to continue all the way down to SK1, sk2, all the way down to sk squared. And here, these are all sample covariances with obvious sample variances on that diagonal matrix. So question, S is a random variable matrix, so this is a random matrix, and obviously sigma is a parameter matrix, and one appears to be an estimate for the other. So, as you should already know, the expected value of Sij is equal to sigma ij. So if you apply the expected value on every element of this random matrix S, then one should be able to easily prove that the expected value of the sample covariance matrix is actually equal to the parameter matrix sigma. And that is a very, very beautiful result. Now, obviously we have several different point estimates for our parameters. In particular, we're going to have, if we have a k by k matrix, that means we have k squared random variables to consider here. We have to estimate all of them, right? So a wonderful lower and upper bound for each of them is the following. In particular, let us assume that you're interested in estimating, for example, the covariance between random variable j and random variable k. And let's assume that you have the sample standard deviations of the individual variables, right? So one can show that the covariance between j and k is actually bounded below by the product, the negative product of standard deviation sj and standard deviation xk. And then the upper bound is going to be equal to, and let's actually use si and sj so these k for the size actually doesn't conflict with itself. I think that's better. So in particular, let's call it si, sj, and then covariance between sij. That's going to be less than or equal to the positive product of si and sj. Right? So keep in mind this is a covariance, and this is just a product of standard deviations of those particular variables, right? So for example, Sj is the standard deviation of the random variable xj, which is obviously just going to be equal to the square root of the variance of xj, right? So that's a very, very beautiful theorem that can construct bounds for approximations of those covariance terms. Now, let us also assume that these sets, or these random variables xj, xj plus 1, xj plus 2, all the way down to, say, xk, do not have a zero variance. So in particular, let us assume that si and sj are both not equal to 0, i.e. these standard deviations are strictly positive. Now keep in mind, the only way that you can have a zero variance is if all of the elements in that particular set are the same exact element. So let's assume that we're not working with those particular sets, else this obviously isn't going to work. So if this is the case, then I can divide both sides by si, sj in that last expression, and I'm going to have minus 1 is less than or equal to the covariance sij divided by the product of si and sj, and that's obviously going to be less than or equal to positive 1. Right? So if that is the case, what I'm going to do is I'm going to define this interior term to be a new random variable, right? Because obviously Sij, Si, and Sj are going to be parameters associated to some random variables Xi and Sj. So what I'm going to do is I'm going to define Rij to be equal to this covariance divided by products of variance. And since these are associated to samples, they are indeed random variables, and therefore this is a random variable as well. And obviously, in case this notation, again, is still new to you, this is sort of equivalent to the old covariance of xi with xj divided by the standard deviation of xi times the standard deviation of xj. So that would be an equivalent notation. Right? So this is obviously a random variable, and obviously it should be approximating something. So this is an approximation for the parameter sigma ij, because that's what Sij is approximating, and that's obviously going to be approximating sigma I and sigma j in the bottom. And some people will denote this as rho ij, or the population, what we call correlation coefficient. So these are known as correlation coefficients. And obviously, when we square them, that's usually what we call the coefficient of determination. And we've spent plenty of time with R squared values with regression. Now, question. Is the expected value of the random variable Rij, is that equal to rho ij? Is that true? Well, obviously, the covariances are unbiased estimators of each other. The variances are unbiased estimators of each other, but not the standard deviations. Keep that in mind. So is Rij an unbiased estimator for rho ij? The answer actually is no. Right? Now, although we often approximate Rij to rho ij, it's not an unbiased estimator. Therefore, there are obvious alternatives for that, which one may explore, right? But let us just keep the story quite brief, and just let's continue talking about the Rij, and we can consider alternatives for estimators of rho ij a little bit later. So what we're going to do is going to define a correlation matrix, which we've actually discussed quite briefly when we want to analyze the explanatory variables of a multiple linear regression model. We're going to be defining the correlation matrix to be the matrix R, and this is going to be equal to 1, R12, R13, down to R1k, and then R21, 1, R23, down to R2k, and this is going to continue all the way down to RK1, RK2, RK3, all the way down to 1. And in case you aren't sure why these 1s are here, because the correlation between a variable and itself is always equal to 1, right? So, obviously some things that you should know is that the correlation between I and j is equal to the correlation between random variable j with I. And therefore, if that is the case, that means that the transposition of the matrix R is equal to itself. Therefore, the correlation matrix, just like the variance covariance matrix, is also a symmetric matrix as well. So when you start analyzing this matrix R, you have all those tools behind you to use. The next thing I want to introduce is a couple common variance metrics that are often associated to random vectors, and obviously there are several other variations that I'm not going to mention, but since random vectors, at least in this discussion, is quite new to our discussion, let's just introduce some of the basics. But before I get into that, let's just define the trace of a particular matrix. Sometimes people will just abbreviate this as TR of A. For a square matrix. So the trace of a matrix is defined to be equal to the sum of the diagonal entries of that particular matrix A. And some people may also write that as the sum from k is equal to 1 to m of AKK, where, for example, A is an n by n matrix and is consisting of all these elements, A, J, K, where J ranges from 1 to n, and K also ranges from 1 to n as well. So just a little baby calculation. Let's assume that A is the matrix 5, 2, 3, and 7. And someone asks you what is the trace of this particular matrix A. So the first thing to identify is obviously the diagonal entries in this. So the trace of A is going to be equal to 5 plus 7, which is going to be equal to 12. Therefore, that is the trace of that particular matrix. So let's introduce the first metric of variation for a random vector, and this is called the total variation of a random vector. Some people just call it total variation, but in particular we're talking about the total variation of a random vector x. And let's also review that x is just a random vector consisting of random variables x1, x2, and let's also continue down until xk. Right, so recall that the covariance matrix for this particular matrix or this particular vector x is given by sigma 1 squared all the way down to sigma 1k, the covariance between variables 1 and k, And that obviously has sigma 2 squared all the way down to sigma k squared. And that has, for example, the covariance between variable k and variable 1. And obviously we have this particular structure. Agreed? So the total variation is actually only interested in the diagonal elements of our covariance matrix. So obviously the trace of our covariance matrix is just going to be equal to sigma 1 squared plus sigma 2 squared all the way down to sigma k squared. So the trace of the covariance matrix is actually just the sum of the variances of each of these random variables in this random vector. So we can obviously write the trace of sigma to be equal to the sum from j is equal to 1 to k of sigma j squared. Right? So this matrix, the trace of sigma, is sometimes referred to as the total variance of the random vector x, which I'm just going to represent as VAR superscript t for total variance, where here x is a random vector, not a random variable. But obviously, if x is a random variable, obviously a random variable is a random vector with only one row, and obviously the variance of t will just be equal to the variance of that random variable, so this notation actually works out. So that's the definition of the trace of sigma, but keep in mind that sigma is a parameter matrix, not a random variable matrix, right? Because the trace of a parametric thing also should be a parameter, right? So in particular, the variance of a random vector is equal to a number, right? Because remember, sigma is just a bunch of numbers, right? So it's a parameter matrix. So obviously we need to approximate the trace of sigma, right? So take a guess of what we're going to approximate it with. So keep in mind, S, which is the sample covariance matrix, was S1 squared all the way down to S1k, all the way down to SK1, S2 squared, all the way down to SK squared, right? So that's our sample covariance matrix. So again, parameter matrix, random matrix, because they depend on the samples. And from here, we can clearly see that the trace of S is going to be equal to S1 squared plus S2 squared all the way down to SK squared, which obviously is just going to be the sum from j is equal to 1 to m of Sj squared. And we already know that S1 squared is an unbiased estimator for sigma 1 squared, S2 squared is an unbiased estimator for sigma 2 squared, and Sk squared is an unbiased estimator for sigma k squared. Right? So obviously, we should be able to prove with quite ease that the expected value of the trace of S is going to be equal to the trace of sigma. Right? So if that is the case, that means that this is an unbiased estimator for this. Right? So the trace of this random matrix is equal to the trace of that parameter matrix, which is actually quite nice. Now notice that this total variance metric, which is pretty much what we're looking at here, because this is just another way of the expected value of the total variance of the sample matrix X, which actually I'm not even going to write how you would write that because, the conversation sort of speaks for itself. But notice that it does not deal with the covariance terms in this particular matrix. That is, it totally ignores, for example, SK1 versus sigma K1. So the generalized variance sort of picks up where the total variance leaves off. So this is called the generalized variance for a random vector x, and this is going to be equal to the following. So the general variance of a random variable x is going to be equal to the determinants of the variance covariance matrix. And one can say, well, obviously that's going to be a parameter. It's just going to be a number because we're taking the determinant of a parameter matrix. And obviously that's going to be a random vector. What are you going to approximate that with? So one could ask, well, obviously I'm going to approximate that with the determinant of the sample covariance matrix. And the next question then becomes, is the determinant of S, an unbiased estimator of the determinant of sigma. If you know some linear algebra tricks in terms of determinants, then you should be able to sort of explore this on your own, but I won't answer this question for you, and I'll sort of leave you with that question to sort of think about. The last thing I want to talk about today should actually be quite familiar to you because we've actually been using linear combinations of random variables for quite a while, starting with, for example, the central limit theorem, chi-squared f, t random variables, and all the sorts of and things in between. So let us see if we can look at this from a vectorized approach and see if we can get anything new out of it. So let's assume we have a vector, a random vector, that consists of all of the random variables of interest, x1, x2, all the way down to xk. And let's assume that we have a series of constants, let's call it c, and let's assume that this is equal to c1, c2, all the way down to ck as well, where each of these cj's belong to the set of real numbers with no limitations on their value. So let's consider the linear combination y, which is equal to c1x1 plus c2x2, all the way down to ck xk. Can we represent this in terms of matrices instead of this long drawn out form? Well, you should remember that this is another way of writing c1, c2 down to ck dot product with the vector x1, x2 down to xk. Therefore, this obviously is just the transpose of the vector c times the vector x. So therefore, this, when we see it, y is equal to ctx, is just a linear combination of the random variables x1, x2 down to xk. All right, now notice a couple things that are actually quite neat. Let's do the expected value of y. So if we look at this from expanded form, it's actually quite easy because it's just c1 times ex1 plus c2 ex2 all the way down to ck exk. And that's going to be equal to c1 mu1 plus c2 mu2 all the way down to ck mu k. But this should look familiar as well, because that's just equal to the same constant stored in the vector c times the parameter vector mu. So obviously we didn't use any vectorized versions to prove that connection, but maybe we can actually use that from the vectorized perspective in the first place. So that means when we look at the expected value of y, which is just another way of saying the expected value of ctx, notice that CT in some self is a constant, right? So we're sort of trying to get comfortable with expected values and variances on vectors of things, right? So obviously in some sense that can factor out. Therefore this is just going to be equal to CT times the expected value of the random vector x, which we have already proven to be equal to CT mu. So it would be the vectorized way of sort of going about that thing for which we've actually been doing all this time. It's just a nice shorter way of writing it. So again, let's consider y is equal to c1x1 plus c2x2 all the way down to ckxk, and let's see if we can actually find a nice way of writing the variance of this linear combination. Now you may remember this from before as being quite annoying. In particular, this is going to be c1 squared times the variance of x1 plus c2 squared times the variance of x2 all the way down to the ck times the variance of xk, and that's it as long as x1, x2 down to xk are all pairwise independent random variables. But if they're not, then you have a bunch of plus 2 times the covariances of the C, let's write that in sort of expanded form. In particular, let's say Ci, Cj times the covariance of Xj, Xj's, and all permutations of these terms. right? Which is actually quite annoying. But what I actually want to do is not actually look at this from the 2 perspective, because that actually makes things quite difficult because it creates a triangular system, not a square system, which is sort of hard to build from a matrix perspective. I actually want to just write it as, for example, 2 times C1, C2 times the covariance of x1, x2. I actually just want to write that as, C1, C2 covariance of x1, x2, and then I want to treat C2, C1 covariance of x2, x1 as different terms, even though they are equal. Because we already know that our variance covariance matrices are symmetric matrices, so they already contain values that are equal. We already know that. So separating these to be equal but different things in some sense is actually quite okay and actually quite recommended when you try to vectorize some of these basic principles. So when we look at this, what do we have? Well, that's just going to be equal to plus C1, C2 times the covariance of x1, x2 plus all the way down to C1, CK times the covariance of x1, xk. And then we're obviously going to continue that all the way down to, for example, CK-C1 times the covariance of xk, x1, which obviously is the same thing as that term. We've already sort of talked about that. And obviously this is going to continue all the way down to CK times the covariance of, not CK, but CK minus 1 and CK. CK minus 1 and CK, right? Yeah, so life is good. K minus 1 and xk. Right? Now, obviously, I almost tripped myself up on that, right? Because notice that we're sort of missing the covariance of x1 with x1. We're missing the covariance of xk with xk, but actually they're up here, right? And it's just C1 times C1, C2 times C2, right? Those are sort of the diagonal entries. So these are the diagonal entries of this expression. So technically everything is here, right? Which is actually quite beautiful. So that means we can write the variance of y in at least double sum form as the sum from I is equal to 1 to k and the sum from j is equal to 1 to k of ci, cj, covariance of xi and xj. Because everything is there, and that's the double summation representation of that expression. But we already know that the variance of x is equal to sigma. And we already know that sigma contains all of the values in this covariance of xi, xj term. So the only thing that we sort of need to introduce is these constants and sort of rearrange them in this expression. So what you can do is we can rearrange this because they're all real numbers, and that's perfectly fine to do. I is equal to 1 to k and j is equal to 1 to k. We can write that as, for example, ci times the covariance of xi, xj times cj. And this representation, although equivalent, will make the next step a little bit more useful, because you should be able to verify with some basic matrix algebra that the variance of y can actually just be represented as C transpose times sigma times C. And this is just the variance of a linear combination. So every time you just see, C transpose capital X, where capital X is just a random vector, that's just a linear combination of those random variables in that vector. And every time you, for example, see a CT sigma C, that's just the variance of a linear combination of those random variables in that particular vector C, where C are typically just some arbitrary constants for which we seek to find, right? For example, those are the beta hat 0, beta hat 1, down to beta hat k in our multiple linear regression model. Right, so that is the variance of y, which is equal to CT sigma C, right? Obviously, no big deal there. And obviously, this symbol, variance of y, can also be represented as sigma squared y, right? That's also another way of writing the variance of the random vector Why? Because keep in mind that in some sense, this is a vector, this is a matrix, that is a vector. This also is going to be a k by 1 vector as well. Right, so this is just going to be a k by 1 vector as well. So obviously we need to approximate this parameter vector with something. So what are you going to approximate it with? So you can approximate, for example, sigma y squared with, for example, sy squared. And sy squared is just going to be equal to ctsc, where S is the sample variance covariance matrix. And you should also be able to prove from this definition where this S obviously is the same S such that the expected value of S is equal to sigma, right? So obviously that's why we're choosing S as an approximation for sigma here, right? So that's a trivial truth. Now, let's consider two different linear combinations of the same random variables x1 and x2 down to xk, which is actually perfectly reasonable. Because sometimes when you want to sort of create a budget with the same exact variables, you have different things that are sort of controlling them. For example, you have a cost and a revenue associated to the same exact variables, but the coefficients associated to each of these variables for revenue and cost are quite different, right? So it's perfectly reasonable to consider two different linear combinations of the same exact random variables before you actually try to fit a model to that. So let's create two linear combinations, which I'm just going to abbreviate by LC for short. Let's assume that y1 is just going to be the sum from I is equal to 1 to k of ai xi. So that's our first linear combination, which obviously can be represented not x1, xi. So that's obviously another way of writing ATX once you define A to be the vector with A1, A2 down to AK. And let's also define, for example, Y2 to be equal to the sum from I is equal to 1 to K of, let's create some new constants, say BI xi. And if we define all these constants, B in a vector, that's obviously just going to be the same as B transpose X. Right? So y1 is one linear combination, y2 is another linear combination. And let's assume that we want to analyze the relationship between these linear combinations, which is actually perfectly okay. Because if x is a random vector and x is a random vector, obviously y1 and y2 will be random vectors as well. Therefore, we should be able to consider the covariance between these random vectors, just like we did with the random variables x1 and x2, for example. So one can show, for example, that the covariance between y1 and y2, which some people will just abbreviate as sigma y1, sigma y2, will just be equal to the double sum of the AI bj times sigma ij, or in expanded form, that's just the sum from I is equal to 1 to k, the sum from j is equal to 1 to k, of AI bj times the covariance between xi and xj, right? And obviously we're going to be approximating that, which is just another way of writing, again, sigma. Oh, I already wrote it there. Sigma y1, y2. So we're going to just approximate that with, for example, sy1, y2. And this is going to be equal to, again, the double sum of ai bj times sij, which is obviously just going to be the sum from I is equal to 1 to k, the sum from j is equal to 1 to k of ai bj times the sample covariance. I guess we don't really have another notation, so I can technically just leave it like that because you know what I mean for that. So that would be the sample covariance between these linear combinations, y1 and y2. And you can also consider, for example, the correlation between these linear combinations. So for example, as revenue increases linearly, does cost increase linearly or decrease linearly, or does it increase in some other nonlinear form? I don't know. But the correlation coefficient can at least answer the linear correlation question. So we can consider, for example, sigma y1, y2, or rho y1, y2, not sigma, which is just going to be equal to sigma y1 and y2, y1 and y2, which is just defined up here, divided by sigma y1, sigma y2, And obviously this is going to be approximated by what we will abbreviate as R, y1, y2, which will be equal to, again, sy1, y2, which is defined here, divided by sy1 and sy2, which is again the sample standard deviations of the linear combination variables y1, which obviously have within them the variances and standard deviations of the individual vector random variables x1 down to xk. Right? So these ideas are definitely nested within themselves. So it's definitely useful to sort of work out little numerical examples with small vectors just to make sure you understand the underlying concepts and what we're actually doing here, such that we can just stay in the more higher level of abstraction to sort of be able to solve more complex problems with these vectorized ideas. So those are some of the basics associated with the vectorized version of statistics fundamentals, and also some basics associated to random vectors as a whole and linear combinations of them. Hope you enjoyed this video, and I'll see you in the next one. Take care.